Right. So back to our activity, we were trying to find out the parameters required under approach one from the datasheet. We needing armature inductance, armature resistance, armature inductance, back EMF constant, and the torque constant. Sorry. So for three, it was not a back EMF constant, but the method of specifying back EMF constant. Let's fire up the datasheet. Do we have something called armature resistance? Once again, that would be a no. We have something called terminal resistance. So terminal resistance would mean armature resistance. Why? Because only the armature has a coil or a winding, and the field is provided by a permanent magnet. So there's only a single coil within this motor, and that's the armature. And so the resistance across the terminals would be the resistance across the armature. It should mean it's zero point 0.6 ohms. So the second parameter we need to find would be once again the armature inductance, which you have previously found. And the last one would be the torque constant or the back EMF, or if it's available, defining the back EMF constant. So, so you can select what to specify through this dialog box option. I see the value torque constant over here, so that's why I selected torque constant. But even back EMF constant is available as well. But in this particular datasheet, it's quite supportive one. But in some datasheets, you won't always see all these parameters. And based on what you see, select the method of specification. So I have selected torque constant, and that would be 25.3 millinewton meters per ampere, and that's what I would be inserting in the dialog box. So once again, since I have made the assumption, made the probable or reasonable assumption that Dr. Damping parameterization in our particular activity or exercise would be insignificant, I'm not going to look for these values and specify them. I'll leave it the parameterization over here. Right. So that ends this activity. We have parameterized our motor using two approaches. And if you want, we can follow the third approach as well. So the advantage in having multiple approaches is that not all data sheets are supportive ones like this. And in some data sheets, especially in motors developed and sold by very unreputed or emerging brands, they may only specify a few of these characteristics, and that's the case for motors like 775, where you can only find the stall torques and the no load speeds and the nominal voltage. And in such cases, having multiple options for parameterization is quite advantageous, since based on what we have, we can select the model parameterization method and plug in the values that we have. So that's it for TNDC motors. Let's move on to how to parameterize stepper motors. Well, in stepper motors, you don't have multiple options for parameterization. Just a single list, and you have to specify every single characteristic in this list. So I'll open up. We have an activity for this case as well. We'll open up the datasheet and we'll dive into it. So for our activity, we'll be needing to parameterize a stepper motor under the series mine be 7 pm series, and the specific motor that we are looking at is KA39B. It's a bipolar stepper motor with a rated current of 1 and a holding torque of zero point 0.6 Newton meters. This one. So we'll be needing phase winding resistance, phase winding inductance, a torque constant, detent torque, magnetizing resistance, and full step size. So in before we move on to finding these values, there's one thing I want to mention, and that is these bipolar stepper motors that we are dealing with in this exercise have once again permanent magnets in order to generate the field. So there's only one winding, and that's for the stator of the motor. Right. So we need the resistance for the phase winding. So do we have that particular term over here? No, there's only something called resistance. And recalling what I told you earlier on, there's only one type of winding in permanent magnet. Sorry, in stepper motors, and that's for the stator. So resistance would mean the resistance across the stator windings, and that is what you should input for phase winding resistance. With inductance, once again, find something specified for inductance, and that would be for the phase winding, 15.9 milliamps. Then you have to find the motor torque constant. So that's not straightforward. You don't see anything called motor torque constant specified in stepper motors, unlike in the PMBDC motors. So we'll leave it right now and move on to the other parameters, and we'll come back to it later on after we have found the others. So we need detent torque, and that's specified in a straightforward manner. Find it and put it into the dialog box. We need magnetizing resistance. It's not specified in the datasheet, but if you take a look at the MathWorks help page, MathWorks has advised us to keep it at infinity regardless of the motor that we are using, as long as it's a stepper mode. So specify it to infinity, just type INF, and then you would be good to go. You'll be needing the full step size, and that's once again the step angle, and that's specified in a straightforward manner. The step angle would be how much of an angle the motor actuates when a pulse is given, as long as micro stepping is not being used. As long as full stepping is used, step angle would be the angle the motor would actuate upon receiving a pulse, and that's what required by the full step size characteristic parameter. Okay, so we haven't found motor torque constant yet, and we'll take a look at how to find it now. So it's not available in a straightforward manner. We'll have to find two parameters and do a small calculation in order to find the motor torque constant.